Good morning, ladies and gentlemen of Precalculus. Today we're going to be working on mostly logarithmic equations and what kind of equations are related to logarithmic equations. And a logarithm is a kind of what? It's a kind of exponent. That's the word. You were going to say it, Justin? I was looking for somebody to say it. Okay, that's fine. And so to me, of the exercise sets we do in this class, to me this is one of the most interesting ones because you're going to kind of see how these things we've been talking about in logarithms and exponential functions have some real world application. So to me that's the interest in this. And the first set here, from 39 to 44, we're introduced to something that I've talked about briefly, like in a video we showed, which is an order of magnitude. Now, order of magnitude is one of those things that a lot of people just like to use loosely and figuratively, right? But the order of magnitude has an actual mathematical definition. And what is that definition? Can anybody figure out what that actual definition of order of magnitude is?
A mole, right?
A mole?
Yeah.
Well, it's related to that. Okay, an order of magnitude has to do with a factor of 10. So something that is 10 times greater than another thing is said to be one order of magnitude higher. And so in this instance, problem 39, we look at these, we have two amounts of money, right? So what are the orders of magnitude that separate these two quantities, one dime and $100 bill?
3.
So Robert says 3. Let's go ahead and check this order of magnitude. And this, according to Robert, 3. Well, let's check this out. So if we take dime, and everybody knows that a dime is 10 cents, right? I mean, is $0.1, and we multiply that by 10, we get $1. So this would represent this change from a dime to a dollar. That's one order of magnitude. And then if we take that $1 and multiply it by 10, what do we get? $10. And then finally, if we take this $10 and multiply it by 10, we get $100. And so here we have 1, 2, 3 orders of magnitude greater. So Robert is correct on that account. Okay? Now I'm going to give Robert some credit for that. I want you to go ahead and work on number 40, and I'm going to spin a wheel in a minute on that, okay? Cooperation. Okay, here we go. We got everybody here. All right, here we go. We have problem 40, problem 40. Chloe, this thing likes you. The wheel likes you, Chloe. The wheel has good taste in liking good people. All right. All right, Chloe, what do we got here? Two. Okay, let's work this out. Now here we have, it's kind of like the last problem, we have a difference in units, right? So unit conversions. Anybody know what a kilogram is?
About 1,000 grams.
1,000 grams, right? So if we take 20 grams and multiply it by 10, what do we get? 200 grams. And then if we take this 200 grams and multiply it by 10, what do we get? Equals 2,000 grams.
Wait, so it's always gonna be by 10, right?
Which is the same as 2 kilograms. So I'm counting 2 orders of magnitude here. Does that sound right? And some of the ones we're going to look at are going to take a little explanation as we go. So this is very much a learn as we go sort of thing today. All right, let's go look at number 41. And like yesterday, we may not get to all these today. In fact, I think for sure we won't get to every single one, but we'll get to most of them. Okay, many orders of magnitude of quantities differ here? Now, the thing about it is these are Richter scale measurements are based on a logarithmic scale and a log base 10 scale. So can anybody guess what our order of magnitude difference between these two is? Okay, order of magnitude between these two is going to be 1.5 because these are log base 10 differences. So we would say that log 7 minus log 5. So log or log base 10 of 7 versus log base 10 of 5.5, right? And if we have this, does this look familiar here?
Yeah.
So 10 to the power of x equals 10 to the power of 7, right? Does that make sense here? And likewise down here, we have 10 to the power of x equals 10 to the power of 5.5. So we have x is equal to 7, x is equal to 5.5, and the difference between those two, that's our order of magnitude of 1.5. Do you have your calculator? You have your calculator? Mm-hmm. I need to get your calculator. Okay, now let me see what this next one is. Yeah, I think this one has a similar sort of a thing, so I'll just go ahead and choose somebody here. And I know it's not as clear, maybe you guys just a couple.
Roberto.
Roberto, great. That's going to be Justin.
Every time. Are you guys like?
Okay, I realize that it's not. This is not as crystal clear. Justin, what do you think for this one?
1.8, I guess.
0.8. That's exactly what it is. Because that is a 10 base scale. We're going to get to more specificity on these types of with the numerical, but Justin's right on that. There you go. Okay. Next. Okay, this one here is a little more challenging. I'm going to choose somebody anyway. I might have to make a correction on that, but I think this is still worth putting somebody on the spot.
It's Roberto.
It's going to be Roberta.
It's gonna be Roberto, I'm telling you.
It'll be Elizabeth, okay.
Actually, I wanted that movie.
Okay, Elizabeth, what do you think for this one? And I realize some of you might, this is sort of learn as we go, that I know some of you will get some of these wrong, and there's a reason for that. Okay. Now basically, based on the patterns we've done in the last few problems, this would be 30. But really the answer to this one is 3. And the reason is because decibels, the decibel reading, and I'm just going to put dB for decibels, is equal to 10 log base 10 of I over I sub 0. And a little later on, and tomorrow, I'm going to show you more what that is. That stands for sound intensity, sound energy, and that's given in watts per meter squared. And this I sub 0 here is I sub 0 equals 10 to the power of negative 12 watts per meter squared. And so what happens is that it's energy, sound energy, that if you cut out a meter square, which is going to be this wide by this tall, that much energy would pass through there. And that's how the sound comes about. And this happens to be what we call the TOH, which is called the threshold of hearing. And in the logarithms in the real world video, this was mentioned briefly, threshold of hearing, and that's the smallest sound that a human being is capable of hearing. So it'd be just like if you could just barely hear a leaf rustling, just the smallest sound you can hear, that's what this amount is, so very little. And then what happens is that 10 decibels is going to be 10 times that ratio, so it's going to be 10 decibels is going to be equal to 10 to the negative 11 watts per meter squared. And then you go up successively in sound, and then you get up to 120 decibels, which is going to be, what's that?
Isn't that like our limit or something?
Yeah, it gets close to the limit. What is 120 decibels? What that's going to be, it's going to be 1 watt per meter squared. And what that is, that's called the threshold of pain. So have you ever gone when there were fire alarms going, and you walk, and it's really loud, and then what happens when you walk right next to that fire alarm?
It gets quiet.
Your ear actually hurts when you're right next to it, right? And then you take another step, and it's still loud, but your ear's not hurting anymore. What happens is, when you get that close, you are experiencing the threshold of pain, where that's actually causing you physical pain. You know what I'm talking about, right? Yeah. And then a real loud rock concert might be 100 decibels. A jet engine, if you're right next to a jet engine it could be like 140 to 150 decibels that will cause hearing damage after a very short exposure. And even a rock concert at 100 decibels, if you go to a rock concert and you go for a couple hours at exposed to 100 decibels, what's going to happen to your ears afterwards? Your ears are going to kind of ring for a little bit, but then your hearing will recover usually. But what happens to musicians or heavy equipment operators that are exposed over a long period of time to that kind of noise? The tinnitus is one of the symptoms, yes. Tinnitus is one of the symptoms of that. And this was really apparent in my own family. What happens, my dad had 3 brothers, and they were involved. My grandfather had a sawmill business in western Montana, where they would actually cut down trees and bring them to a sawmill and so forth. And what happens, my dad was the oldest, so he was sort of when the brothers got together as a crew to work the logs and for the sawmill, my dad was the supervisor. But one of my uncles, Clayton, his duty was to drive the truck. And others, they had other duties, but of the 4 brothers, every one of them had hearing problems later in life, except for Clayton, because Clayton was driving the truck. So was Clayton as exposed to the noise as his 3 brothers? No, he wasn't. So that's what happened to my family. And you know that musicians, rock musicians who don't get in there with the proper hearing protection, they'll have hearing damage over time also. And that's why when I go and I hear, you ever go next to a car and the sound is so loud that you can hear it through 2 pieces of glass as you're going? Do you think some hearing damage is going on there in a lot of instances? Yeah, it is. So just be careful about that. Okay, so Elizabeth, what's going to be our order of magnitude on number 44? It'll be 6. Well, exactly. And what we're going to do is we're going to do the mathematics that really nail down the numbers of that more here as we go, especially tomorrow. We're going to work more. We're going to dive deep into sound intensity. And now we get to exercise 45, comparing earthquakes. And then we're asked the question, how many more times severe was the 1978 Mexico City earthquake with a Richter scale reading of 7.9 than the 1994 Los Angeles earthquake with a Richter scale reading of 6.6. What do you think? We'll work this one out. Oh, what's your sticker? What do you think about this one? Any ideas? How many more times severe?
1.3.
So 1.3 is the difference between these two, and that does have something to do with it, but it's not 1.3 times as severe, it's more. And we talk about severe, we're talking about amplitude. A Richter scale, a seismometer, which measures earthquakes, will have a needle that goes up and down. And the amplitude of that needle is what we're talking about when we say severe. Okay, 13 times. Okay, that's closer to it. I don't think it's exactly that, but I think it's going to end up being close to that. But let's just go ahead and I want to show the arithmetic and the mathematics behind it. What we have is that we have log of a certain amplitude, which is going to be, I'll call this a sub 1 over I sub 0. I'll call it I sub 1. But it's not that. Let's see, I got that wrong because that's, yeah, we're using this. Yeah, we're looking at ratio. But it's going to be 10 log of one over the other, and then minus 10 log the ratio between, let's say, a sub 1 and some base. I'll just call this r right here. And that's going to be equal to 1.3. And it's not going to be 10 actually, that's the sound. So that's what the thing is going to look like. But that's where we get it. And so what we do, can we simplify? Okay, I'm going to say a sub 2. What it is, we'll call this one 2. We'll call this a sub 2 and this one a sub 1. So we're going to have log. Can we combine these logarithms? How can we combine those logarithms that we talked about a while ago using the rules of logarithms? I'll give you more information. The quotient property of logarithms. How do we combine these into a single logarithm using quotient property of logarithms?
A1 minus A2 over R squared.
How do we combine these into a single logarithm? See if I have one of your exercises you did on this. Properties of logarithms. I think that's actually in 3.4, so you probably have your papers on this, guys. No, here it is. So here, Roberto. How about this one right here? How can you combine those into a single logarithm? Okay, this is how you do it. This here is going to be equal to log of A1 over R divided by A sub 2 over R. Right? And what happens when we simplify this? And that's going to be equal to 1.3, and that's log base 10. And so what's going to be a sub 1 over r divided by a sub 2 over r? Well, that's going to be equal to a sub 1 over r times r over a sub 2. What happens here? Cancellations. So what we get is we get log base 10 of a sub 1 over a sub 2 equals 1.3. Can this be changed into another form? Well, yes it can. 10 to the power of 1.3 equals A1 over A2. So what is 10 to the power of 1.3?
19.95.
So we would say about 20 times greater. Right? So we will leave it at that. Okay, and then I'm going to go ahead and call on somebody for problem number 46, which I think is a pretty similar type problem.
I'm going to the office. I'm leaving.
Okay, next one, 46. Nicole just left in time, so I'm just going to click spin.
It's Roberto.
It's going to be Roberto or Becky. It'll be Becky. Okay, Becky, what do you think? Let me show you this.
I haven't all written down, I was just like actually playing some things with it.
So basically what it's going to amount to, it's going to be 10 to the power of whatever that difference is going to be your answer. So
You get 7.2 minus 6.6 equals
0.6, okay.
and then I just did
10 to the power of 0.6, okay, that's what?
3.98.
3.9, okay, that's it.
So about 4 times.
So we'll say 10 to the power of 7.2 minus 6.6 equals 10 to the power of 0.6, did you say? Equals about 3.98, or about, is that right?
Yes.
About 4 times. Yeah, about 4 times greater. So we'll just keep it there for that. And before I did this class today, I went, you know what I did yesterday in preparation for this class?
Watch the video.
I watched the video, especially on 45. Because I promise you, when I have to watch a video to get myself straight on what's going on, and even with that, I don't think I explained it especially clearly. I'm thinking that for 6th period, I may actually just play that clip of the video. I gave a better explanation in the video than I did today live in class, imagine that. Thank you, Becky. Okay, the pH of carbonated water is 3.9 and pH of household ammonia is 11.9. And then we're asked these 3 successive questions. And the first thing is and we're given this formula right here. Now this formula was actually not from the problem in the book, but I think the book is assuming that if you read the chapter up till now, you'd have this formula close at hand, but I just put it here on the paper. And so we're asked, you know what the pH scale is, right? Acidity and alkalinity. And so basically it's a pH scale of reading about 7 is pretty neutral. And the range is from 1, which is very acidic, to 14, which is very basic, which is the opposite. So water that doesn't, and then the liquids that we deal with and consume most of the time are in sort of a tight range of that, maybe between 3 and 8, something like that. Lemon juice maybe being 3 or something like that, and then milk maybe being a little bit more than 7, and so on. But we're going to go ahead and do this. What are their hydrogen ion concentrations? So we're going to find the hydrogen ion concentrations, and this is what we're trying to solve for. So if we go ahead and put in, I'm going to get a skinny pen here. If we go ahead and put in like 3.9 is equal to negative log, and that being log base 10 of H plus, I'm just going to put H plus like this. So this is like a variable that we solve for. And what it has to do, it's concentration of some number of moles per liter of hydrogen ions is what it is. I forget exactly what it is. But how would you solve this equation? How would you solve this equation?
Subtract 3.9. Would you make that side 0?
Well, you know something, Robert says you can make that side 0. You actually could if you were going to solve by graphing, right? But the problem you're going to have is the number is going to be so large that you're not going to be able to see where it hits the x-axis because you're going to be talking about an extremely small number is what it amounts to. So that's why in this case you probably wouldn't want to solve by graphing unless you really had a better idea of where to look. Okay, let's go ahead and we multiply by -1. We get log base 10 of H plus is equal to negative 3.9. And so what we get is we end up getting 10 to the power of negative 3.9 equals our H plus concentration. And what's 10 to the power of negative 3.9?
You get 1.258.
1.258. So maybe 1.26 times 10 to the which power? 10 to the negative what power? Negative 4 power. And so that's going to be the concentration. That's going to be in hydrogen ions per liter or something like that. And then the other one's going to be similar, but it's going to be 10 to the power of negative 11.9. And what's that going to be? 1.258.
To the, like, you can put 1.26 to the negative
Times 10 to the negative
12.
12 power. Okay, so this is going to be for your ammonia. And this one here is going to be for our carbonated water. Yeah, so plain water should be about 7, but with the acid you have from carbonated water, it'll be a little lower than that. How many times greater is the hydrogen ion concentration of the carbonated water than that of the ammonia? Well, we just take 1.26 times 10 to the negative fourth divided by 1.26 times 10 to the negative 12th. And so what's that going to be?
Still on it.
That'll cancel. So you'll have 10 to the 8th. Negative 4 minus negative 12. So that's going to be 10 to the 8th power is what? That'll be 100 million times greater. So 100 million times greater. And then what is the order of magnitude difference? What is our order of magnitude difference here?
8.
8. Okay, just 8 because 8 power. Yeah. Okay. And let's look at this one here. 48. So I'm going to call one more person. We probably, because I don't think we're going to have time to go beyond this day. So we can do Newton's law of cooling tomorrow and do our sound one. So that'll be good for tomorrow. That'll be just perfect. Okay, let's go on for this one. This will be Karina. All right, Karina, this is you. All right, what did you think about this one?
For stomach acid, it would be 0.01.
So we get, what'd you say?
0.01.
0.01. So that would be your concentration. And then what is going to be your,
For the blood one?
yeah, for blood?
That's 3.98 times 10 to the negative
3.8,
98.
3.98, 3.98 times 10 to the
Negative 8.
negative 8. This one here, I'm going to rewrite this one as 10 to the negative 2 power. Can I do that? Okay. And so here they are, that's part A. Okay, now part B, how would you do that one? So 10 to the negative 2 power divided by 3.98 times 10 to the negative 8 power. What is that going to be? Six? Oh, 10 to the 6 power. So 10 to, well, just put that in your calculator, see what that says.
I think it's gonna be 100,000.
Something about that, yeah, around roughly. So 151,000,
No, 200.
or 251,000?
256.
256? So times greater, right? Times. Now I like that Robert had that estimate of 100,000, right? So he had that pretty close. Did you just know that because 10 to the negative 2 divided by 10 to the negative 8 is kind of... How many orders of magnitude? Yeah, so it's going to be 5.4, right? Okay, so that'll be that. So we're just going to leave it there today, and we're going to work on Newton's law of cooling tomorrow. And so I want to thank everybody.